All right, thanks for the introduction. And first of all, thanks very much to the organizers to give me this amazing opportunity. And I will tell you a story from these papers, all in collaboration with my supervisor, Miguel Tierz, and some of them also with Richard Szabo. And also comment on some ongoing work with Roberto, Tateo, and Miguel. By the way, I apologize to a couple of people in the audience who already heard the 10-minute version of this talk, but maybe the longer version will be more enjoyable. This is the plan. It is divided into 3 main parts. I will start with an overview of the perturbation of 2-dimensional quantum field theories by the irrelevant operator TT-bar. And then I will pass to my own contribution, which is the TT-bar-deformation of 2D Yang-Mills theories. And these 2 sections will occupy most of the talk. Then I will discuss another deformation of 2D Yang-Mills that comes from dimensional reduction from 5D, which has been introduced in our paper with Miguel and Richard. And I will conclude with some open problem that might be of some interest. So, okay, let's start with the review part. So very generally, the study of all possible deformations of a given quantum field theory allows us to explore its neighborhood in this vast space of theories. Eventually, we would like to understand as many deformations as possible for as many QFTs as possible, so to get a chart of this enormous space of QFTs. But this is, of course, a way too ambitious program, and so we have to be smarter in our pursuit. So it is more instructive and much more useful in practice to focus on a distinguished property of our theory and characterize all deformations that preserve that property. Now, we would like such property to be strong enough to allow for computations, but we don't want it to be too rigid, because otherwise we would be exploring an empty manifold. A good choice could be conformality. So we start with a CFT, we study all its exactly marginal operators, and explore the conformal manifold. Another powerful choice is supersymmetry. So we start with a superconformal field theory and study all deformations that preserve all or a fraction of the supersymmetries. Nonetheless, throughout most of the talk, the preferred property would be, of course, integrability. In this context, irrelevant deformations of 2D quantum field theories by the composite operator TT-bar have attracted a considerable amount of attention since the work of these 2 groups here back in 2016. This operator is defined essentially as the determinant of the stress energy tensor in 2D and with complex coordinates with point splitting regularization and also up to total derivatives. Now, it is clear that we are building our deformation out of the stress energy tensor, so it exists in a QFT under very, very mild assumptions. As I said, the original motivation to study this object is integrability. Indeed, Smirnov and Zamolodchikov have shown that given an integrable QFT, there exists an infinite countable family of operators that have the property of preserving integrability. And TT-bar is the lower spin representative of this family. TT-bar, moreover, is singled out as special in some sense because it is solvable, by which I mean that we can write down the flow equations, solve them in closed form, and find explicit expressions for the deformed quantities as functions of the original initial quantities. And this is true for the Lagrangian, for the energy levels, for the S matrices, and for partition functions on compact spaces such as the tori. Since its introduction, TT-bar has found a broad variety of applications, including, of course, integrability, but also holography, both in the context of ADS3 deformed CFT2, but also turning on the operator in the bulk theory living in ADS2. Also supersymmetry. Now we know in which supermultiplet this operator sits in, and so on. Also perturbations by generalized irrelevant operators, both the higher spin relatives of TT-bar, as well as other double trace deformations built out of different conserved currents. It has also been applied to non-relativistic field theories, spin chains, and so on. So in the past few years, there's been really a lot of literature on the subject. So this is, of course, not a lecture on TT-bar, so I can't be comprehensive. You will apologize me. Please refer to the papers for more adequate citations. And if you want to learn more, there is a nice review by Jiang, or there is a review by Givion if you're interested in the connection with string theory. Another remark is about conventions. I will follow the ones in the paper I co-authored, which are the same as in this other paper here. In particular, I will call the deformation parameter tau. Of course, it's sometimes called alpha or lambda. This is not relevant, of course. Some numerical coefficients won't be relevant. But as we will see, the sign will be important. So just to make clear what type of conventions I'm following. So as promised, let's study the TT-bar-deformed quantities, starting with the Lagrangian. We can write down a flow equation, and we want to solve it with the initial condition, of course, that at zero deformation, we recover the initial Lagrangian. So I've written here the solution for a bosonic model found by Conti, Anella, Negro, and Tateo. There are also solutions for fermionic models in a paper by Bonelli, Drud, and Zhou, also supersymmetric models. So it's quite well understood by now. And as we see, we have a square root singularity for any positive tau, which is a signature of a non-local quantum field theory. Now, this is a generic solution, but we can study simplest cases by splitting the Lagrangian in various pieces. So we can start with non-dynamical fields. So the initial Lagrangian is a pure potential, and the deformed Lagrangian has this expression, which is fine classically, but we have to make sense out of this if we want to plug this inside a path integral. On the opposite side, we can take a single free boson without any potential, and in this case, the deformed Lagrangian is the one for Nambu-Goto with a three-dimensional target space. It is known that Nambu-Goto is a theory of strings, so already for a single free boson, we see how non-locality comes about. We identify the string tension with the inverse of this coupling tau, and so at zero value of tau, we have a string which is infinitely tense and behaves like a point particle. However, for any finite positive value of the deformation, we have extended objects, and so our effective QFT will be non-local. Another object that we can follow along its RG flow is the energy levels once we compactify on a spatial circle. Their flow equation is a Burgers equation of implicit type with a source term given by the momentum. So we could try to write down a flow equation also for the momentum, and we found out that this is a constant. But this is, of course, what we expected, because the KK momenta on the circle are quantized, so they cannot evolve continuously. So obviously, they cannot be perturbed. Then we solve the Burgers equation for the energy, and we find two solutions corresponding to the two branches of the square root. But once we impose the initial condition, we uniquely fix our solution, which is the one with plus sign. So we have a square root here, so we see how important is our choice of sign, because for any negative tau, we can find a state which has highly enough energy for which this deformed energy becomes negative. So for any negative tau, we will have a loss of unitarity. There is a holographic proposal to understand this breakdown of unitarity given by these three gentlemen that suggests that the TT-bar-deformed CFT with negative coupling should be dual to ADS3 with a radial cutoff that goes with the inverse of this coupling tau. So highly energetic states in the CFT side correspond to BTZ black holes on the dual side. So we see that for a negative tau, we have a finite cutoff. And if we go highly enough in the energy levels, then we find larger and larger black holes until we hit a black hole whose horizon reaches the radial cutoff for any negative fixed tau. And so we see that we cannot have unitarity beyond that point. This is not quite the end of the story for holography. There is a much more powerful derivation by Gica and Montonen, but I won't discuss this any further, but please refer to their paper and following works for more details. The other object that you can follow along its RG flow is the S matrix. It in fact is modified in a very simple way because it simply picks a tau-dependent phase, which is a so-called CDD factor. And actually, among all allowed CDD factors, TT bar corresponds to the simplest as possible. But we won't need it, so I won't discuss this any further. And let me discuss instead the Torus partition function. So it is very well known that the partition function of a CFT on the torus is modular invariant. Also, we can write down our flow equations with respect to this parameter tau for the partition function of the TT-bar-deformed theory, and it is a diffusion equation for this Torus partition function. It turns out that the partition function of the TT-bar-deformed theory is still modular invariant, which is quite striking, of course, because the theory is not conformal anymore. But not only this, but in fact, we have a uniqueness theorem. So if we start with a CFT and list all its irrelevant deformations and ask how many of them preserve modular invariance, it turns out that there is only one, which is in fact TT-bar. So it's quite a strong result, if you ask me. Also, the Torus partition function allows me to introduce something called a non-perturbative ambiguity. So we have this diffusion equation for the partition function of the deformed theory, which has this generic solution. So we have a perturbative part in this coupling tau, plus a non-perturbative part, which is bound to be of this form for some function x of tau. So for positive tau, once we impose the initial condition, so we go towards tau equals to 0, but from the positive side, this non-perturbative part blows up. And so once we impose the initial condition, this additional function x must vanish, must be equal to 0. Instead, if we approach the tau equals to 0 from the negative side, this non-perturbative part is, of course, non-perturbatively suppressed. And so we do not have any initial condition for this additional function x. And so we have this so-called non-perturbative ambiguity whenever tau is negative. Also, we all know very well this famous triangle of relations that makes Einstein happy, which connects the stress energy tensor, geometry, and gravity. So we are building our operator out of the stress energy tensor. So we can imagine that it has something to do with gravity and geometry. But for TT-bar, we can make this connection very precise, very explicit. So at classical level, TT-bar is the same as a field-dependent redefinition of variables. Also, but only at linear order, so we need to stay close to our initial QFT, TT-bar is equivalent to coupling the theory to a randomly fluctuating geometry with Gaussian fluctuations. And also from the work of Dubowski-Gorbenko and Mirbabai and Dubowski-Gorbenko-Hernandez-Shiflet, we know that TT-bar is essentially equivalent to topological gravity. As I will make more precise now. So the breakthrough insight from this paper is that the TT-bar-deformed QFT should be equivalent to the original undeformed QFT coupled to two-dimensional topological gravity in the first order formalism, by which I mean that we write everything in the Weilbein formalism and then integrate over maps from the worldsheet geometry to the target space geometry. This first order formalism is important. So in flat space, this is essentially the same as JT gravity, but of course with a fixed target space topology. However, if we want to generalize this, there are some subtleties because we always need to pass through the first order formalism and the equivalence is not so clear or not so well proved. So that's why I will call it a topological gravity. So we know that the path integral in this case localizes onto constant metrics, and also that the integration over the dilaton field is very simple. It is just a Lagrange multiplier which enforces a flat metric constraint. So from this perspective, we have a new handle on the exact solvability of TT-bar, which can be a sort of alter ego of the one loop exactness of topological gravity. And in this gravity formalism, we can reproduce all the like the Burgers equation and all these features that were first proved by direct solution of the flow equation. So questions so far? All right. So let me discuss the new part, which is the TT-bar-deformation of to the Yang-Mills theories. Like as a very imprecise and generic motivation, let me say that if we are willing to introduce some non-locality feature in our theory, we might want to study them at first in a theory that doesn't have any propagating degree of freedom, and this is the case of 2D Yang-Mills. Yes, please.
excuse me, probably this is very something stupid, but the transparent, before you go ahead, as I said, this is probably a stupid question, but often when you are one loop exact, then you may have instanton corrections.
On the JT-gravity side, you mean, or on
no, I mean in the other, in other kinds of theories. For example, the prototypical example probably is not the case. It's just, you know, something that crossed my mind.
Yes, I think so.
So
in
like
general, yes.
n equal to in 4 dimension for it. This is the most famous case. It is one loop exact, but then you have the instantons corrections.
Yes.
But probably there is nothing like this here. I don't know.
Okay,
I have
so
no clue.
I'm not an expert on JT gravity, so I'm not sure. But what I can tell for sure is that to have this equivalence with TT bar, you don't consider any non-perturbative correction to the gravity side.
Yeah, probably.
Otherwise,
yeah,
you
probably
get the same. I don't know
it.
if there is a possible thing because we are in flat space, so it's in fact a very simple case of JT gravity. So I don't know the generic answer, but for what concerns TT bar, for sure you don't have to take them into account if there are.
Okay, probably, yeah, probably.
But thanks for the question. So let me start with a very brief review of Yang-Mills theory. I know most of you know it very well, but just to put everyone on the same level. So we start with the Yang-Mills action. In 2D, we put it on our Riemann surface sigma. So we have the usual Yang-Mills action, but in 2D, we can write this in this equivalent form, which is true in 2D once we exponentiate the action and plug this inside a path integral, because in 2D, the Hodge dual of a 2 form is just a scalar, so we can write this equivalently. So we already see some noteworthy features of 2D Yang-Mills. For example, that any Yang-Mills theory or some deformation of it is equivalent to a BF theory, which is this term, which is topological, plus a certain potential, which in principle is quadratic, but the generalization is really straightforward. We also expect some dependence on the volume form from the left-hand side. I'm sorry, some dependence on the metric from the left-hand side. But from the right-hand side, we see that the dependence is in fact very simple, and we just have this simple dependence on the volume form. Also, for 2D Yang-Mills, the path integral localizes and reduces to a finite dimensional expression, which is in fact a discrete matrix model. So I've shown here the expression for Q Yang-Mills that I will define in the next slide. If you only want ordinary Yang-Mills, just forget about the Q. So the sum is over irreducible representations of the gauge group. Dim Q is the so-called quantum dimension, which is a 1-parameter deformation of the usual notion of dimension. Chi is, of course, the Euler characteristic of our Riemann surface. Q is the deformation parameter as before. P is an integer which counts the degree of a certain line bundle on sigma, but we can analytically continue it to any positive real value. And C2 here is the quadratic Casimir. So this equation, this expression is often called the Migdal or Migdal-Rusakov formula, well, at least for ordinary Yang-Mills. And it was first derived using the self-reproducing property of Yang-Mills in 2D. So we can take a tessellation of sigma, solve the theory on a single tile, and then we glue various tiles together, and what we find is just the same expression on a larger area. And this is what allowed Migdal to found this expression first. But there are other ways to obtain this expression, for example, by Witten's cohomological argument, which is essentially a non-abelian localization theorem. And also there is the abelianization approach by Blau and Thompson, which is the one that most easily extends to the TT-bar-deformed setting and the one we adopted in our paper. So here's the family picture of this family of Yang-Mills theories. We can start with the BF theory and add a potential and land on Yang-Mills or some generalization thereof. But we could also first modify the path integral measure and only then add the potential. And in this case, we land on the so-called Q-deformed Yang-Mills, or Q Yang-Mills for short, or some simple generalization thereof. And then we can also refine the theory and get something more intricate. There is another derivation for Q Yang-Mills, which is in fact the original way it appeared, which comes from type 2A string theory on a Calabi-Yau threefold X. So we take a stack of D4 branes on a certain non-compact 4 cycle, which is this total space of a degree P line bundle on sigma. And then we ask what is the word volume theory on this 4 cycle. And it turns out that this is topologically twisted n equals to 4 super Yang-Mills in 4 dimensions. However, in this simple case, it reduces to 2D on sigma to a simple deformation of the ordinary Yang-Mills, which is indeed what we now call Q-deformation or Q-Yang-Mills. So anyway, let me discuss now the TT-bar deformation of it. So Yang-Mills theories in 2D are almost topological, by which I mean they only depend on the volume form, as I showed earlier. So they are especially well suited to study TT-bar deformation using the JT gravity approach. Okay. So we have to replace the volume form everywhere by writing it in the dynamical Weilbein and then integrate over these Weilbeins. There is actually a technical subtlety that we have found that, however, seems to be ubiquitous. It appeared in other works by Tolley or some works by Shyam and collaborators. And that is the normalization of the gravity path integral cannot be, let's say, the naive one, but it really must be theory dependent. Otherwise, if once we take the tau going to 0 limit, we wouldn't reproduce the initial undeformed quantities. So in some sense, and let me very not rigorously, we may think of this gravity path integral as a sort of defect filling the space-time of our theory, because it's really must be dependent on the theory. Anyway, this is just a technical aspect and we can live with it. So we can TT-bar deform our Yang-Mills theories. So we start with a BF theory. It is topological, so we can cut sigma into elementary pieces which are diffeomorphic to disks with known 1 or 2 holes. Then we turn on the potential and Q-deformations and refinements if we want. And since each component is flat, we can use the equivalence between TT-bar and JT gravity and turn on the topological gravity. Of course, the BF part is topological, so it does not couple to the gravity path integral. Now, why are we doing all these things? Well, because as I said, the equivalence between TT-bar and topological gravity is only proved in flat spaces. So we really want to cut our surface into flat components and see what happens. Of course, for such a simple theory, we could expect that directly plugging the path integral of gravity in curved space doesn't change much. And in fact, that's what we find, but we didn't want to conjecture it. We wanted to prove it. So we have solved this gravity path integral, very simple, and we find this deformation of the potential, which is of course what we expected. We have also proved that harmonization persists, and that at the end we can safely glue back all the pieces together with no obstruction, putting the TT-bar deformed theory back on our curved spacetime sigma. So this is the final answer for the partition function of Q Yang-Mills. Is essentially the same as before, except that now we have a deformed Casimir, which is essentially a geometric series in the Casimir. Now, a couple of remarks on this expression. Well, first of all, it has been obtained by other authors prior to our work, first by Conti, Iannella, Negro, and Tateo, and by direct solution of the flow equation, and later by Ireland and Shyam, and both in the case of ordinary Yang-Mills. But both solutions were in some sense conjectural because they assumed that we had a matrix model and then they plugged the TT-bar deformation at the matrix model level. Instead, we have started with the full-fledged path integral, solved the gravitational path integral, and proved that the beionization persists. So really, in this way, we could generalize this to other theories such as the Q-deformation and refinement, and proving that the two deformations are consistent. Also, we might be worried about some singularity here in the denominator. First of all, let me say that if we take a larger limit, this is a perfectly well-defined convergent geometric series. Also, we might have some problem at finite n, but remember that for positive tau we don't have a non-perturbative ambiguity, so we should be able to expand the exponential of this object in tau. So we don't, and we get a perturbative expansion, but we don't have the non-perturbative ambiguity in this case. So we should get the same answer. And also in this special case in which we get a matrix model, there is yet another way to make sense out of this expression. because it's customary in matrix models to take a potential with infinitely many couplings and then turn off all but finitely many of them at the end. So we could turn on infinitely many couplings in the potential here, then expand a formal geometric series. And in this way, we renormalize all couplings to each order. And then instead of turning all couplings but finitely many to 0, we have to fine tune them so that eventually we truncate the series. So this is some sort of very non-generic procedure, but we can do that and make sense out of this expression whenever we have a matrix model. Anyway, I've shown you the, yes.
Can I see the previous expression for your partition? Yes, for the potential. You choose there in particular dependence on n in your tau.
Yes.
Is there a way to understand why you choose n
yes.
to the third
yes,
not
indeed there is in fact a way you know in advance how you must scale tau with your coupling. So generally you can write tau, but then for example we are interested in the large n, so we need to figure out how does tau scales with n in our case. But this is very generic because for example in the recent paper by Roberto and others, they want to study a non-relativistic limit on a theory, so the large parameter is the speed of light and the scaling is the same. But so we have a 1 over n cube because actually we should have a gauge coupling. So I already set it in Toft units, so it gives.
So you basically have in mind the Toft limit at the end of the day.
Exactly.
And this is the correct scaling for having a good Toft limit.
Yes, but not only the Toft limit, but in fact in any limit, there is an equation in the paper by Continental, Negro, and Tateo, and from that it's very generic. It does not depend on n because it's like this generic bosonic expression. And from that, you can read out how tau must scale when you take some parameter large, and you know that tau must go as 1 over the square of that parameter. So I get an 1 over n square and another 1 over n because I'm just working in Toft units. So that's how I get this number.
Okay.
But thank you for the question. All right. So that was the expression for the partition function, but we can in fact take some decorations on sigma, so for example boundaries or punctures or Wilson loops, symmetry defects. Everything goes through in the same way. So I've shown here a correlator of Wilson loops, which might not be so interesting, except the fact that this is the same expression as for Q Yang-Mills without TT bar, but we simply get this change in the Casimir. So our motto is that TT-bar-deformation preserves abelianization, or stated differently, TT-bar does not spoil the cohomological nature of our Yang-Mills theory. However, despite being so nice and so mild, TT-bar still spoils some of the main features of our theory, most notably the factorization of the partition function into chiral and anti-chiral sectors. It is a large n feature of ordinary Yang-Mills, but this is exact in Q Yang-Mills. I will only discuss the ordinary Yang-Mills for simplicity, but the argument can be extended. So we can go to a free fermion formalism. So our Yang-Mills in 2D is equivalent to a theory of fermions on a circle. And the factorization takes place at large n because the upper and lower Fermi surfaces decouple in the large n limit. However, we see as soon as we introduce the TT-bar deformation, we get non-local interactions between these fermions, and so this prevents the factorization at large n. Another property that is lost is the connection of Q Yang-Mills with Chern-Simons theories. So for Q going to 1, or more generally Q going to a root of unity, Q Yang-Mills converges to Chern-Simons theory on the length space LP1, where P is the same integer as before. However, as soon as we turn on TT-bar, we lose this connection both with Chern-Simons or any sort of deformation of it. So another very well-known aspect of Yang-Mills in 2D on the sphere is that it undergoes a large n third-order phase transition discovered by Douglas and Kazakov, and the transition is induced by instantons. The same is true for Q-deformed Yang-Mills, and the Q-deformation enhances the volume of the weak coupling phase in parameter space. So if you remember that parameter P, we can decrease it from infinity, and the weak coupling phase will be enhanced as P decreases. And eventually the weak coupling phase, the volume blows up at p equals to 2, so there is no phase transition from that point below. Then we have studied the larger limit of TT-bar-deformed ordinary Yang-Mills on the sphere, and we have found again a third order transition, again induced by instantons. But the TT-bar-deformation reduces the volume of the weak coupling phase. So as I said, once we take the larger limit, the geometric series is really convergent, so we can expand our Casimir at large n in a geometric series. And so once we want to study the equilibrium equation, we find essentially the same as Douglas and Kazakov, except that we replace the Casimir in a geometric series. So we can solve this perturbatively in tau, and we see that at each order we simply get the same solution as Douglas and Kazakov, but with a renormalized area. And in fact, we can go on and eventually solve this to all orders in perturbation theory. And we find that the area is renormalized by a positive coefficient larger than 1. So we see how the weak coupling phase is reduced because the area becomes larger by the TT-bar deformation, and so it reaches the critical value earlier. But we can also look at the instanton suppression factor. So once we turn on the TT-bar deformation, it is deformed in such a way that it vanishes earlier in parameter space, and so instantons are released earlier in parameter space, and so we have a phase transition earlier. After our work, there has been some more interest in large N Yang-Mills with TT-bar deformation by this Russian group who adopted a collective field theory formalism. So first of all, they found that at large N, this collective field theory has deformed energy levels that satisfy the real Implicit-Burgers equation. So this might sound obvious, but it is not trivial or straightforward because we are taking our Yang-Mills theory in 2D, we TT-bar deform it, and then we take a collective field theory as a tool to study this theory. And so it is nice that we get again the Burgers equation, but it's not obvious from what I said earlier. They have also rederived the phase transition at positive tau, and they have given a non-perturbative computation of the renormalization coefficient of the area. And they found that it agrees perfectly with our all-order perturbative computations. But this is what we expected because, as I said, for positive tau, there is no non-perturbative ambiguity. So the two approaches should be equivalent. And so this is a nice consistency check. Also, they found a first-order phase transition at negative value of tau. And this is really due to the non-perturbative ambiguity that I mentioned earlier. So this is a picture from that paper that I stripped off and zoomed in. So tau becomes more negative towards the right. And the orange curve is the perturbative part of the partition function, the one which is smoothly connected with the positive tau regime, while this blue dashed line is the non-perturbative contribution. And so we find here a first-order transition at negative tau when this non-perturbative contribution to the partition function takes over. So the non-perturbative contribution, the ambiguous one, becomes the dominant one. So we can redo the same type of computations for Q Yang-Mills and its refinement, and we again find a third-order transition, again induced by instantons, and the volume of the weak coupling phase is reduced compared to Q deformation and enhanced compared to TT-bar deformation. So both effects combine nicely. The proof we have given is essentially, as for ordinary Yang-Mills, we give this all-order computation, and we can again look at the instanton suppression factor, and we find that the Q deformation and TT-bar deform it in different sectors, in different ways. So we see from there why these are compatible, the transitions. Also, we have found that as soon as we turn on TT-bar, the transition is extended below the value of p equals to 2, and that we can go to lower and lower values of p, and eventually we can push the transition all the way down to p equals to 1. So if you remember, P had a geometric meaning. So first there was a sort of distinction between certain geometries and all the other geometries for P larger than 2. But once we turn on TT-bar and wait enough along this RG flow, we do not see any distinction at all between geometries in some sense. All right. So at this point, we may ask what happens if we add a Higgs field to the story. So it is known that Yang-Mills Higgs in 2D is equivalent to its supersymmetric version, which is n equals to 2,2 star. Gerasimov and Shatashvili have shown that there is a correspondence between the UN gauge theory and the n-particle sector, the n-particle wave function of nonlinear Schrödinger. And this is one of the simplest instances of what is called Bethe gauge correspondence, which has been extensively studied by Nekrasov, Shatanshvili, and collaborators. But remember that our main motivation beyond the introduction of TT-bar was that it preserves integrability. So we may ask what happens if we turn on TT-bar on both sides of the correspondence. And this is a work in progress with Roberto and Miguel. So we have worked out the two sides separately, and we have found that the correspondence survives in this TT-bar-deformed setting. And this, in fact, is true for a slightly more general class of theories, but we do not have a very general proof yet for all these Bethe gauge correspondences. But there is a clear class, a subsector of these correspondences for which it survives once we turn on TT-bar. So this is a nice test of TT-bar, in my opinion, because it does not only preserve integrability directly on our integrable QFT, but in some sense, it also preserves it across dualities, if you want. So, questions? Okay. So now let me discuss a different type of deformation of Yang-Mills.
So what's the correspondence of the deformation in the Bethe side?
The Bethe gauge correspondence, you mean? So yeah, this has been extensively studied by, there are many papers by Nekrasov, Shatanshvili in 2009. Oh yeah, you mean how does, so the fact is that there is a class of theories for which the TT-bar deforms some parts, but do not deform the part that enter the correspondence. So for these theories, of course, we have been able to show that whenever some assumptions hold, TT-bar does not deform this part that enters the correspondence. And so for this subclass of theories, we know that it survives. For other theories, we do not know yet because there are some technical difficulties or subtleties. So yeah, more generally, it might affect the part that enters the correspondence. So we have still to work harder for that. So does this answer your question? Thanks. All right. So let me discuss this other deformation, which comes from dimensional reduction from 5D, and we called it a squashed Q-deformation because it comes from a reduction on a squashed sphere. At this stage, you may think that it has nothing to do with TT-bar, but hopefully by the end of the talk, I will convince you that it has nothing to do with TT-bar yet, at least. So let me first remind you of or introduce you to Gaiotto dualities or 2D 4D dualities. So the idea is to start with a maximally supersymmetric 6-dimensional CFT and compactify on a Riemann surface with a topological twist. In this way, we get a 4-dimensional n equal to 2 theory that is called of class S. And by construction, this should be dual to a topological theory on sigma. But we can then put the 6D theory on this geometry, which is sigma cross S1 cross S3. So we get this 4D theory on the geometry S1 cross S3, which computes the so-called superconformal index. And it has been shown by these authors that the 2D theory that is dual to the superconformal index is Q Yang-Mills on sigma. So a first question is, we can invert or change the order of compactifications, and we should be sure that we get the same answer. And indeed, we first reduced to 5D super Yang-Mills on S3 cross sigma, and by a direct localization computation, we have found that in fact we get the same result as Tachikawa and these other people for Q Yang-Mills on sigma. Then we may ask what happens if we deform the 5D geometry by squashing the 3-sphere. And this way we get a simple modification of the result, which we call squashed Q-deformation, because as I said, the one parameter deformation is just the same parameter that is deforming the geometry. And I've shown here the partition function, which is a nice matrix model because it is discrete, it is Q-deformed, and also because of the B squared inside here, it is a so-called B-orthogonal ensemble. So this is a purely 2D part, plus certain contributions that in some sense remember that we come from 5D, but these are non-perturbatively suppressed in the regime we are interested in. So the squashing parameter plays a role similar to the P as for Q Yang-Mills, and in fact the partition function I've shown earlier is very similar, but not quite the partition function of the refined Q Yang-Mills. So if we go to large n, we have essentially the same as the refined Q Yang-Mills, but for finite n, there are some differences. And in particular, we find a connection with Chern-Simons theory on much more general length spaces, because now we can take B squared, which in principle is real. Well, in principle, yeah, it's positive. We can take it to rational values, and we reproduce Chern-Simons theory on the length spaces LPS instead of only LP1 as we had before. So now let me conclude by mentioning some open problem and connecting the two aspects I have discussed. So a first question is, why should we care about this type of theories? And to answer, let me first give a small preamble by paraphrasing two people much more knowledgeable than me, that are Yifan Wang and Edward Witten. So at this stage, we might expect that to make some progress in string theory, we'll need to understand non-local deformations of 2D CFTs. And TT-bar seems to be a very good starting point, because it is a non-local deformation, but it is solvable. So it will give us some handle on this difficult in general deformations. On the other hand, I believe that most people in this room would agree with me that integrability is a very powerful guiding principle, both in strings and field theories, that allows us to establish sometimes surprising connections between very differently looking theories and also across dimensions. I've also mentioned I already mentioned the Bethe gauge correspondence, but I think also most of us will think of the planar integrability of n equals to 4 super Yang-Mills. So eventually, we may try to understand or find out some RG flows in higher dimensions that are as solvable as TT-bar is in 2D. So we may ask, once we have a 2D theory with a known duality or correspondence with a higher dimensional theory, and we turn on TT-bar on the 2D side, what happens on the other side? Does this correspondence survive along the RG flow? And if so, what is this unknown deformation, this black box operation, in this case, a white box operation, on the dual side, on the higher dimensional side? So I believe that Yang-Mills into this are good starting place to ask and answer these questions, because as we have seen, it is tightly related to four-dimensional gauge theories. First of all, Q Yang-Mills, by its very definition, descends from n equals to 4 topologically twisted super Yang-Mills. We have also seen that it appears in theories of class S, and also Yang-Mills, the ordinary Yang-Mills in 2D, appears from localization of n equals to 4 theories with defects. It has been already told yesterday. So we may ask what happens if we turn on TT-bar on the 2D side, and if we are able to pull back the deformation to 4D. It's a hard problem, but hopefully we may start to understand this. Of course, this is not the only way to proceed. An alternative approach would be, for example, to leverage the recent developments in understanding TT-bar deformation of spin chains and try to learn something from that about four-dimensional n equals to 4 super Yang-Mills. There could be another approach to follow. But let me make this very clear. So there have already been attempts to generalize TT-bar to higher dimensions. But, and of course, there are various ways to lift an operator to a higher dimension that then is projected onto TT-bar. What I mean is not really that. I'm suggesting something different, which is we work in 2D with the original TT-bar, the one we understand, and try to understand some dual operation in some higher dimensional theory that might have nothing to do with TT-bar in such dimension, but which mirrors or is a sort of avatar of what we are doing on the 2D side of the correspondence. So anyway, I would say that in the past few years, we have learned a lot about TT-bar deformation, in general irrelevant or non-local deformations, but it's likely that we are just scratching the surface of a very deep and interesting subject that probably deserves further attention and further investigation. So that's all I wanted to say for today. Thank you very much for your attention.
Thanks. So, any questions from you?
So you mentioned in your motivation that that would be interesting for sort of non-local descriptions as appearing in string theory. So what class of worldsheet theories could you apply this to? Can you apply this to, say, the worldsheet theory describing string theory in ADS3, or what family of theories would your techniques apply to and allow you to study what TT-bar-deformations would do?
Well, that was just a generic remark that in general, vacua of string theories are 2D superconformal field theories. So there have been some recent developments in the understanding the TT-bar-deformation of this of generic n equals to 0,2 or 2,2 superconformal field theories. So hopefully this will give some understanding of some deformation of some vacua of string theory, but hopefully we can extend this understanding more generally, but I don't have like a clear prescription for now. Sorry.
On the same line of this question, there is, as you certainly know, a string description of two-dimensional Yang-Mills. There is the famous Gross-Taylor description in the 90s. It is probably the first time in which a gauge theory has been shown exactly equivalent to a string theory in the larger limit. So what about your deformation in this context? As you know, there is a weak phase on the sphere that has no string interpretation. There is a strong phase that has a precise string interpretation, maybe also more precise in the Q-deformed sector. And did you ever explore the fate of the TT-bar-deformation in this kind of string theories, or is it possible?
Honestly, I've tried, but without much success, but it should be possible in principle. So yes, also in the paper by Ireland and Shyam, they try to give a sort of this expansion a la Gross-Taylor for the TT-bar-deformation, but I think what they found is not very conclusive. So they suggest that this should correspond to a certain deformation of the corresponding string theory, but I think it is not very, very clear what this deformation should be. In my opinion, as you said, if we go to the Q-deformed Yang-Mills, this should be, well, more difficult because we have one more parameter, but the interpretation in string theory should be clearer.
Yes, so, because you have a topological string theory behind.
Yeah, sure, it should be clear, but, and honestly, I've looked, but I didn't succeed so far, but it will be a very interesting matter.
Thanks.
Thank you.
Yes, so question from.
So I would like just to make a remark about the last question. Okay. Any two-dimensional field theory can be represented as a sum of random surfaces without folds. And the only difference, say, between the TT-deformed theory and the continuum theory with the second Casimir as the action, is that the weights will be a bit different. So these surfaces will contain branch points, and they will have different weights. But the sum, the measure, will be more or less the same. And I would like also to remark about the partition function of the gauge theory on a surface with arbitrary genus. The relation with Migdal is not direct. It was a problem solved solely by Rusakov, and the problem was given to him by Volodya Kazakov.
Okay, thanks for the remark. I didn't know that. Thank you.
Yeah,
I know that what you say about the weights, but I don't know if, I mean, if there is an understanding of what would be the string theory effect that would, I mean, some sort of operator in string theory that produces this effect. So we can study it from the gauge theory side and mimic the Gross-Taylor expansion, but I don't know if we have a first principle derivation from the string theory side. I don't believe so, but I might be mistaken. I don't know. Oh, no. Yeah.
I mean, the only thing I wanted to say is that there is a sum of random surfaces, that corresponds to any two-dimensional gauge theory. But maybe the simplest one is that of Gross-Taylor, that then considered by Gregory Moore and.
Okay, yeah, right.
Yeah, thanks.
Yeah, thanks for the remark.
So I didn't.
Hello. I just have a curiosity. I wanted to ask whether the TT-bar deformation necessarily destroys the ultralocality of the Poisson bracket of the Lux pair in case it is there, like for the nonlinear Schrödinger model. Do you always end up with a non-ultralocal Poisson bracket?
Good question. The answer is, I think so, but I'm not sure. I don't know if someone in the audience has a better answer than me. But because I haven't really looked into the Poisson bracket, but I think someone knows this better. But sorry, I don't know for sure.
Thank you.
Can I ask the last question about this counterpart in 4D? So you mean you also want to do some operation in the 4D theory, or just a twisting process?
So you mean in the last point or just generally?
The last pointer.
Yeah. So well, what I meant is some sort of middle step in between. Instead of going directly to string theory, trying to understand first, going to 4D and then embed the 4D theory in string theory. So yes, for example, if we try just to couple a 2D subsector of the sphere with JT gravity, we couldn't have localization approaches. So the procedure to get these Yang-Mills theories wouldn't work out. So we have to find another way, maybe a sort of roundabout way to introduce this TT-bar-deformation. So what I had in mind is that if we can figure out some operator on n equals to 4 super Yang-Mills, that we plug this inside our theory, we use the localization machinery a la Pestun, and get, as a result, the TT-bar-deform to the theory. And so in this way, let's say, we know where we have to land, where we have to arrive. So this might give us some insight in where we have to start and how this works. But still, I have no definite answer for that.